Hello, everybody from WCA Physics. This is Miss Peachy, and today we are going to be looking at acceleration in your next lesson here. As I promised you before, I'd be doing a little lesson anytime there is some math involved, and so there is some math involved in this lesson, albeit they are keeping it fairly simple. So acceleration is the rate in change of velocity. So when we look at how velocity changes over time, which we can denote as delta V over time. This is our acceleration. So that's kind of the formula that we use. You can simplify this, or you can, I shouldn't say simplify it, you can actually view this in more detail by looking at the final velocity minus the initial velocity over time was equal to acceleration. So that's another way of looking at acceleration. So it goes on to talk about how velocity is defined as rate of change of an object's position, and that could be speed and or direction, right? So velocity is a vector, so it's both magnitude and direction. The other thing to look at in terms of velocity is that that direction might be positive or negative depending on where you're going. So when we look at direction, we've been talking about directions on the compass, like east, west, north, and south, and angles of relationships like 45 degrees north of east and things like that. But sometimes it's as simple as straight lines, and you can really look at that or think of that as being on a number line itself, right? So if you think about a number line, if I start at a certain point and I walk 2 meters in this direction, and then I move 2 meters or an additional, let's say I go back 4 meters in this direction, my ending position is going to be behind where I began, right? So in this case, my change in position, I start at 2 meters, I end at negative 2 meters. So I start at 0, I end at negative 2 meters. So I would say, so remember this is velocity, so if I say change in displacement over time, I would write that as negative 2 minus 0 over time. So you have to use your final position minus your initial position divided by time, and that can be negative. And that negative in this case is just telling us that you actually move behind you. It's a directional indicator. It doesn't mean you don't have something. Sometimes we think of negative numbers as meaning that we're in debt or we don't have value. And that can be the case when you're looking at like money or certain things like that. But when it comes to position or velocity, that is usually a directional indicator. It's telling us that I move that way instead of forward. I give myself forward as positive, behind me as negative, and so that indicates the movement, which direction that I moved. In this case, my net motion was backwards. That's why we're using that negative number. So don't get freaked out too much by negatives in there. Some people think of negative velocity or negative acceleration as slowing down. That doesn't necessarily mean that. It means a direction that you're traveling. That's what we're using that number to represent. All right, so here we have a graph of position versus time. It says, notice that in the earlier time intervals, position changes very little, and in the later time intervals, position changes more. In our previous exercise, previous lesson, I'm going to actually zoom out on this one a little bit. We had seen linear, a line that was kind of a linear line here. So it would have been looked more like that, right? And that meant that the slope of the line was the same everywhere. So if I measured the slope here or here, it didn't matter. Or if I measured the slope of the entire thing, the slope, the rise over the run was the same for all, right? So here, in that particular situation where the slope was the same, that indicated we were going at a constant velocity. This, with the curve, shows us we're not going at a constant velocity. In fact, our velocity is changing. And we can see that because the slope of the line here is going to be quite small. And as you move upwards, the slope of the line here is quite large. So my velocity here is much greater than my velocity down here. So in this case, this is showing that I'm speeding up. I'm increasing my velocity. And anytime my velocity is changing, we call that acceleration, right? So acceleration is change in velocity, and it can indicate speeding up or slowing down, but it can also indicate change in direction. So that's a bit tricky because sometimes, when we look at circular motion, which we'll look at later, we're constantly changing our direction, even if our velocity remains constant. So keep it in the back of your mind that that can also just mean change in direction and not necessarily change in speed. Okay, remember velocity is speed and direction. So acceleration could be a change in either one of those factors, either speed or direction. But we'll keep that kind of in the back of our mind because right now we're just going to look at the speed part of it. Okay. So this is acceleration, and as I said, we write that as delta v over t, change in velocity over time. And remember, delta v is v sub f minus v sub I. And I always say v sub, meaning subscript. It means it's in the subscript. So v sub f, that indicates to you that it's a component of velocity. It's the final velocity. So whenever I say sub, I'm just making sure that you know it's a subscript. Okay, so now we have a different graph. Now, before our graph was position versus time. So be really, really careful. Pay attention to the y-axis of these types of graphs because you can get tricked if you assume that every graph you're looking at is a position versus time graph or a displacement versus time graph, which is the same thing as a position versus time graph. This graph is velocity versus time. So let's kind of back up a little bit. I'm going to go back to the previous graph just as a reminder. Let's go back to our previous graph. So in a position versus time graph, the y component in this graph is displacement, right? And the x axis is time. When we figure out the slope, that's always y over x. So that is equal to displacement over time, which is basically the same thing as velocity, right? So the slope of a position or displacement versus time graph is velocity. The next graph that we have is a velocity versus time graph. And in a velocity versus time graph, now my y-axis is velocity. That's our slope, right? So we have velocity divided by time. Well, that is acceleration. So the slope of a velocity versus time graph shows us acceleration. So in this situation here, we are accelerating at a constant rate. What does that mean? Does that mean we're going at a constant speed? No, it does not. It means that we are speeding up at a constant rate. The best example I can think of is gravity. So gravity, we say gravity, but when we're looking at a falling object, we're actually not talking about the force of gravity, but we're talking about acceleration due to gravity. So when an object is falling, gravity is pulling on that object, right? And it's pulling at it proportional to the mass of the object. So more mass of the object, the harder gravity actually pulls on that object. But all objects fall at a constant acceleration. So what that means is that if you have two objects and you're Galilei, and you're going to stand at the top of the Leaning Tower of Pisa with your cannonball and I don't know what other ball he used. I don't remember. But he had two different balls of two different masses and he dropped them. They fell at the same speed and they both reached the ground at the same time because they are experiencing a constant acceleration. So it doesn't matter what the mass of the object is, it will fall at the same speed. But what that really means is if I have a cliff here, okay, and I'm going to drop something off of this cliff, a ball. I'm not throwing it, I'm just dropping it, okay? So I'm not giving it any acceleration or any additional, I'm just going to drop it. Let gravity act on it. So constant acceleration would mean that after 1 second, if we measure the speed of that ball, and I'm going to round here just to make this easier math. The ball at 1 second will be traveling at a speed or velocity, if you will, of about 10 meters per second. If I then get the speed of the ball at 2 seconds in its fall, so it's going to be here in 2 seconds, it's now going at 20 meters per second. Now, I can't, it's hard for me to actually to draw this physically. At 3 seconds, it's at 30 meters per second. So it keeps speeding up at a constant rate. Every second in free fall, the ball is basically increasing the rate of its velocity by 10. It's constant. So at 4 seconds, it would be 40. At 5 seconds, it would be 50. That's what we mean by constant. It's not going like 10, 18, 25. It's not like all over the place. It's constant. It's at a very constant rate. And that would be what we consider to be constant acceleration, right? So that it's accelerating at a constant rate. It is speeding up. It's not maintaining the same speed. It's maintaining the same acceleration. What is the acceleration? Well, it's changed its velocity from 20 to 10, so 20 minus 10, and the time is 1 second per 1 second. So if I calculate this out, I get 10 meters per second for every second that it's falling. It changed 10 meters per second for every second. If I look at the next one, same. 30 minus 20 divided by 1, also 10 meters per second for every second. That's the acceleration. The acceleration is always 10 meters per second in this particular example of this ball that's falling, right? So it's constant acceleration. The speed is not constant. The acceleration is constant. We can also write this 10 meters per second as 10 meters per second squared. Mathematically, they're exactly the same thing. We tend to write our acceleration as meters per second squared because it just makes it less messy rather than writing it this way. They are the same. Personally, I like 10 meters per second only because as teaching physics, I think it logically makes more sense. And you can really visualize here that a meters per second is going to be velocity and our seconds are going to be time. So it's mirroring or showing you the equation, velocity divided by time, right? So it's doing a great job of really the units themselves showing you the formula for acceleration. And that's why I prefer that, especially in a physics class. But either or is fine. Okay, so that's what constant acceleration means. And we see that when you have a constant slope on your velocity versus time graph. When you have a slope of 0, which is what we're seeing right here, that means that there's no acceleration. And no acceleration means constant velocity, which makes sense. Our velocity here is 6 meters per second according to the graph at every data point there, right? All of these data points are 666. Oh, that's a bad number. Why did they choose it? I don't know. Hopefully it's a coincidence. But so that means constant velocity, 0 acceleration. So if velocity is not changing, you're not accelerating. Unless your direction's changing, which we're not going to talk about right now, right? We're just going to talk about the velocity component. So as long as your velocity is constant and your direction's not changing, you're not accelerating at all. Okay. Clear screen. How do I do that? Here we go. Yeah. So, I think that's pretty much the gist of this. Oh yeah, there's one other thing that they show you in the last part of this, and that is using, I think, in the very end here. Nope, I missed it. Hang on a sec. Let's practice. Oh, right here. So you can actually use the area under a velocity versus time graph to figure out displacement, which I think is kind of cool. This is something that's kind of a cool thing. So this graph is actually giving you lots of information. So why can you use the area to indicate displacement? Well, let's think about the relationship between velocity and time. So displacement is equal to velocity divided by time, right? So if I have velocity, which in this case we're saying is 2, oh, okay, never mind. I'm sorry. I screwed this this formula up here. I was confusing myself, but velocity, I wrote it wrong and I was like, what? And it was my dyslexic brain. So velocity equals displacement divided by time. That's what we wanted to do. So in this graph, we are given velocity and we are given time. We're not given displacement. So velocity then times time is equal to displacement, right? So that's the formula for figuring out displacement. So basically, we're taking velocity, which is our y component, multiply by time, which is our x component, which is equal to the area underneath there. So as long as we have the area, we can look at the area of this rectangle, velocity 2 times time 3, that gives us that 6 meters for displacement. And the same thing holds true if you're using it on a slope. You can figure out the area under the triangle 1/2 base times height, and again, that's going to give you displacement for this case. So that's what this is showing. I'm sorry, I had that tiny little blub there with a brain fart, but that's fine. So hopefully that all makes sense to you. Hopefully you understand what constant acceleration is and how constant acceleration does not mean you have constant velocity. And you can look at a position versus time graph and make sense of it, and a velocity versus time graph and make sense of it as well. If you have any questions, let me know. Otherwise, thank you guys for watching, and we'll see you in the next one.